Now, you may remember yesterday, one of our examples I did was, I think it was something like, x plus 2 all squared. And I said, well, for now, we're going to have to expand it out. And that's not a hassle, I suppose, with squared, because that's pretty quick to expand out. But if the power was anything bigger, I mean, cubics, yeah, I suppose that's okay. But, it's a bit time-consuming. So we need another way of doing it. This is what the chain rule allows us to do. Now, the formal chain rule is this. U is some function of x. So if you're differentiating some function of x to the power of n, you still bring down the power like we did before, so same as normal, but you also have to multiply by the derivative of what's inside the parentheses. I personally find that a bit confusing, so I just remember it this way. Bring down the power, lower the power, diff the inside. Okay? Think of it like anarchy. All right? So anarchy, you bring down the power, because that's what anarchy is. So you've got some ruler, you bring them down, then you lower the power, so you chuck them on the ground, right? So you really humiliated them, and diff the inside. Well, back in medieval times, you know how sometimes different letters look like different things? And so like a B could look like a D and stuff. So that diff really means biff. So you put the boot in. Right? So bring down the power, throw them on the ground, kick, put the boot in. That's your chain rule. Okay. So here it is. This was the question from yesterday. I say, wasn't too bad to expand out. But what we could now do is bring down the power so the 2 comes down the front. Lower the power so the 2 becomes a 1. Then put the boot in. Diff the inside. The inside is 2x plus 1. Differentiate that. We get 2. And so we get 4 outside of 2x plus 1, which is the same answer as yesterday, just that it's been factorised. Okay. But if you can use this now for higher powers, I mean, power of 7, to expand that whole thing out, it's going to be a bit time-consuming. But bring down the power, lower the power, diff the inside. The inside, in this case, the derivative is 3. 7 3s are 21. It becomes very quick then. I don't have to expand the whole thing out. Okay. X squared minus 10 all cubed. Bring down the power, lower the power, diff the inside. In this case, in the inside, differentiate it, we get 2x. 3 times 2x, 6x. Doesn't matter if there's a number out the front. This time when I bring down the power, I'm going to go 6 times 5. So we'll get 30. Lower the power, 5, diff the inside, negative 2, negative 60. Where it's really useful, I guess, is something like this. Because I can write that in index form, but I can't expand it out. So I really got no choice here. So bring down the power, half, lower the power, negative half, diff the inside, 2x. So I get x outside of x squared minus 3 to the power of minus half. That's how a mere mortal would write their answer. But us super mathematicians, there you go. X on the square root of x squared minus 3. It's basically using this idea. So this is, I prefer to think of the chain rule like this. Right? dy dx, what I'm doing is, instead of differentiating with respect to x, what I'm really doing is differentiating with respect to u. So I'm just calling that one function. And that's why I can still just bring down the power, lower the power. But then I have to multiply by the derivative. This is what we call another way of writing the chain rule. This becomes very useful when we have equations written like this. It's what's called parametric form, where we have x equals 4t, y equals 2t squared. Yes, I could rearrange this, make t the subject, substitute it in, and I would get an equation in terms of y in terms of x. But what I can do here is I can differentiate each bit individually. So dx to t would be 4, to y to t would be 4t, and then to work out dy dx, I can say, well, okay, I haven't got dy dx, but I've got dy to t, and I've got the t dx, so I can play around with those. The dt's, if you like, would cancel. And so I get 4t times the reciprocal of dx to t, and so the answer is just t. So I have my answer in terms of t. If I wanted it in terms of x, I could go back here then and say, oh, well, t is x over 4, so the derivative would be x over 4. Okay. Yeah, I should say that idea with parametrics will come in very handy next term when we actually look at the topic of parametrics. So more on that, I guess.